Hi everybody, Mrs. Pesic here, and we are looking at the rest of section 3.1. We were talking about exponential functions, and so you remember that in general, exponential functions are going to be of this form, y equals a raised to the x. But just so you know, every exponential function, whether it's exponential growth or decay, is going to have one y-intercept and one horizontal asymptote. All right, so when we draw an exponential function, let's say it's exponential growth, it's going to have one y-intercept and it's going to have one horizontal asymptote. There is a summary on page 200 if you want to take a look at some of the other properties of exponential functions. But in general, can we say that an exponential function will pass the horizontal line test? Remember, the horizontal line test is what tells whether a function is going to have an inverse or not, or whether the inverse is going to be a function. Well, in this case, I think we can see that this horizontal line is going to cross through the graph in at most one point. So does an exponential function pass the horizontal line test? That would be a yes. And so exponential functions will have inverses, and I'll say stay tuned. Let's see section 3.2 for that. All right, so they are one-to-one functions and they will have inverse functions. All right, we looked at a few of these yesterday. So just to kind of recap, I think this is on your gift. For if we have 4 raised to the x minus 2, that's going to be a shift right 2. All right, and if we're shifting a graph to the right 2, let's say there's our function and we're shifting it to the right 2, that's just going to, that's not going to work. We are going to shift it to the right 2. That's going to just shift it over a little bit like this, but that's not going to change the horizontal asymptote that we have, right? This next one is a shift, since we're taking the opposite of the whole function, that's a shift, no, I'm sorry, not a shift, take it back. That is a reflection over the x-axis, all right? And if we reflect over the x-axis, then the graph's going to be looking something like this, but then that's not, again, going to change the horizontal asymptote. Let's take a look at this next one. We've got 2 transformations here. Again, another reflection over the x-axis, but now this is going to be a vertical compression of 1/2. Again, no change to the horizontal asymptote, still going to be y equals 0. This one has a negative here with the x. That's going to be a reflection over the y-axis. All right. So if I look at a graph like that, that is going, here's my parent function, but if I'm reflecting over the y-axis, then that graph is going to look, something like this. Okay, that's reflected over the y, but we also want to shift that graph up 3 units. So if I shift that graph up 3 units, then the horizontal asymptote is no longer going to be at, y equals 0. It's going to be up here at y equals 3. So this one right here was a shift up 3, and our horizontal asymptote equation would then be y equals 3. For all the others, it was y equals 0. All right, so we already talked about how the y-intercept is going to change for many of these, and we talked about what the horizontal asymptote was going to be. All right, so we talked about the natural base in class, and we talked about some applications, and we were doing these problems in class. Let's get to this one, because I'm not sure if we got an answer for this. So this was continuously, again, it was $25,000 invested, so we want $25,000. By the way, we're using, for compound continuously, we need to use this PERT formula, as I will call it. So we want 25,000 times e raised to the rate, which was 0.0825, and then it was 26 years. So that's the equation that we are going to use. So if I grab the calculator, I get 25,000 times, I'm going to use this e to the x button here, and I want 0.0825 times 26. And why was I doing that on the graphs page? I have no idea. Let's go to a calculator page and try that again. I want 25,000 times e to the 0.0825 times 26. That looks better. So about $213,000, $213,551. All right, so that would be our answer for this one. And let's go on to this next example. So in your book, and I really encourage you to look at page 205 in your book, they have example 9, all about Chernobyl. And so if you know anything about Chernobyl, there was a nuclear power plant called Chernobyl, and in area of Russia, Soviet Union at the time. And so let's take a look at some of the issues. Now, this website that I'm pulling this up from is old. I mean, this is from 2011, which was the 25th anniversary of the Chernobyl nuclear disaster. But I just think it's really fascinating to look at some of these things. All right, and to talk about, I mean, this is leading into exponential decay and half-life. So that's why we're looking at this. So if we just look at a couple pictures here and get a little history lesson. So this first picture is talking about, you know, the desolate town of Pripyat. Okay, on April 26th, 1986, this amusement park was being readied for the annual May Day celebrations when the Chernobyl nuclear reactor exploded less than 2 miles away and severely contaminated tens of thousands of square miles. So here's just a few of the photos. So this is the city of Pripyat, once inhabited by 50,000 residents, but now it is just a chilling ghost town. Built in 1970 for the scientists and workers of the nearby Chernobyl nuclear power plant. Authorities did not warn residents of the accident and issued an evacuation notice only 2 days after the explosion. So they really let people, you know, they were trying to hide what was happening. So here's what exactly happened. At 1:23 a.m. on April 26, 1986, the Chernobyl nuclear power plant operators committed a fatal series of errors here in the control room of reactor 4, triggering a meltdown and an explosion that resulted in the world's largest nuclear accident to date. Now, that was in 2011. Since then, there's been another very, very serious nuclear accident in Japan, maybe about 5 years ago or so. In this picture, they say workers wearing plastic suits and respirators for protection paused briefly on their way to drill holes for support rods inside the shaky concrete sarcophagus, a structure hastily built after the explosion to isolate the radioactive rubble of reactor number 4. So I think this is fascinating that these workers, you know, they got to monitor their Geiger counters. They're so concerned about the radiation, and they're only allowed to work one shift of 15 minutes per day. That's how dangerous it is inside. And these pictures just kind of show, you know, how nature has taken over in this ghost town. Basically, this is a school where, you know, you can see the trees have started basically coming into the classroom. This is just showing, you know, some of the people have hastily left things lying around as they evacuated. And a lot of the people are sick, you know, that live there. I mean, people, you know, they have thyroid cancer and so forth. So this is just, you know, kind of a, you know, it's just some of the pictures of the people. At least this was 25 years later. So these pictures were taken in 2011, so about 8 years ago. All right, so let's talk about what to do with and how this ties in with exponential functions. So if you can look at example 9 on page 205, which is about Chernobyl. But actually, I have one example that I want you to do, and this is the example that is on your gift, I believe. I'm checking. Yeah, so 1,620 years. So this is on your gift. So it says, let Q represent the mass of radium, whose half-life is 1,620 years. The quantity of radium present after T years is given by this function. Q equals 16 times 1/2 raised to the T over 1620. And first thing is, let's determine the initial quantity when T is equal to 0. So if I plug in a 0 here, I will get Q equals 16 times 1/2 to the 0 over 1620, which is just 0. Well, I know that 1/2 to the 0, anything to the 0 is just 1. So I get 16 times 1. So the initial quantity was 16, right? I don't know if this is in grams or what. We'll just assume grams maybe. The next thing is sketch the graph over the interval from 0 to 5,000. So let's use our calculator to do that. So if we're going to graph this equation, now I'm going to add a graphs page, and I want 16 times, and I want 1/2. Well, I'm just going to use, I guess I'll use 1/2, parentheses, and control divided by 1/2, and I'm raising this to the fraction out here. I want t, but I'm not going to use t, I'm going to use x over 1620. And so I'm not seeing the graph. Let's play around with the window. So if I go menu, window zoom, window settings, and I know that I'm only interested in, what's happening from like the 0 to, and I think they said 5,000. So let's have this go to 5,000. And I know, let's say our minimum is, y minimum is 0. And we just saw that our y maximum is going to be 16, right? Because that's the initial amount, and it's going to be decaying. Oh, we didn't talk about that. How do we know it's going to be exponential decay? Because this number here, that's our base, and our base is between 0 and 1. That's exponential decay, right? So I know that there's going to be a decaying graph. So here we go, 0 to 16 for our y's. And there's our graph. Sure enough, it does look like exponential decay. And then the follow-up for this, and again, if you're doing this on your paper, you're going to pick some points. You may even want to make the left side here of your axis, the y-axis, and make the very bottom of your graph the x-axis. Okay, so getting back here, so it says we sketched it. Well, you're going to pick some points, maybe do Control T and pick some order pairs. Actually, I probably wouldn't do that. I would probably actually, let's see what we can do. Let's go back to Control T again, get rid of this. I would actually maybe go to a calculator page. If I go to a calculator page and I just type in, what was this? This was F2. So if I just type in, I want F2 of, and put a parentheses, F2 of, let's say, 0. We already knew that that was going to be 16. F2 of, let's say, 1,000. What happens after 1,000 years? Okay, then there's 10.4. So I could make my increments go by 1,000 or go by 200 or something. And if I try F2 of 2,000, I can get that it's down to 6.8 and so on. So go ahead and plot some points for your graph. And basically you want to get out to 5,000. So maybe you're going to say, oh, I'll make this 1,000, 2,000, 3,000, 4,000, something like that. I'll let you be creative with that. All right, and then it does say how much will remain after 1,000 years, and I think we just answered that. That would be this 10.4 are going to be left after 1,000 years. All right, so that concludes this video. Thanks for watching.